Okay, this is a video on Newton's law of cooling. Okay, here's a question as to be solved. A. To find the temperature of the thermometer after T minutes, use Newton's law of cooling. It states that the temperature U of a heated object in a given time, T, can be modeled by the function U of T equals capital T plus the initial temperature, which is U of naught, minus T, capital T, parentheses, capital T representing the temperature of the surroundings. E times E raised to the kt power, k being the exponent, the rate, and the t being time. So where capital T is the constant temperature of the surrounding medium, U of naught, which is like a little zero or O or something, is the initial temperature of the heated object, and K is a negative constant. Use the formula U parentheses lowercase t parentheses equals capital T plus parentheses U of naught minus capital T parentheses E raised to the kt power. So in other words, it's saying the temperature, the final temperature, is going to be taken by figuring out K and then inputting values for T to get U of T. So first I have to solve for K. And I'll start by plugging in values that I know, which already I know 39 degrees is the temperature of the surroundings, so I plug that in for capital T there. And then I have the initial temperature, which is like U of naught, and I plug that in there also. So I have U of T equals 39 plus parentheses 11 minus 39 parentheses E to the kt power. So I simplify that to U of T equals 39 plus negative 28 to the E raised to kt power. So it's U of T equals 39 minus 28 E raised to the kt power. Now I'm going to try to get K by itself, so the first thing I'm going to have to do is to do so to get K by itself, I'm going to start plugging in values for the little t next. So like time, also the little t for time, and the little and the ut for the temperature after a certain number of minutes, because I already can figure out the cooling rate because they already gave me some variables to plug in. They told me that after it started off, the thermometer started off at, 11 degrees, and the surroundings is 39, but they said here that after 5 minutes it have warmed up from 11 to 12 degrees. So I can plug in that value for little t to help me solve for K. So now I have U of T, which is 12, equals to 39 minus 28 E raised to the K of 5, K fifth power, like K, which is a constant, and then fifth power. So to solve for K, I'm going to have to divide both sides. I'm going to first have to, what is it? I have to subtract, to get rid of the 39 first. Subtract 39 from both sides and simplify. So I have subtracted 39 from both sides, which gave me 12 minus 39 is negative 27, and the 39 minus 39 cancel the now. Gave me negative 27 equals negative 28e raised to the k5 power. So now I also have to divide the negative 28 on both sides to try to get try to isolate k. So I have divided both sides by negative 28, meaning that negative 27 divided by negative 28, negative divided by negative equals positive. Gave me 27/28. And also I divided negative 28e raised to k5 power divided by negative 28, which just left me with e raised to the k5th power. So now I have 27/28 equals e raised to the k times 5 power. So now I have an exponent, and I'm going to have to rewrite that as a logarithm. So to rewrite that as a logarithm, I just have to rearrange the values I already have. So here I have e. Here I'm raising e to this power to give me this value. So I know that the e, another way to write the e, which is the base in this case, is to write ln. Okay, so ln here represents e. Ln is going to be, after being raised to the k5 power, which is here on the other side here, k5 ln, which is e raised to the 5k power, is going to equal 27/28. So this raised to this is going to equal this. This raised to this is going to equal this. Now I have 5k equals ln 27/28, the natural log of 27/28. I want to get k by itself, so I divide both sides by 5. So in this case, I multiplied the natural log of 27/28 times 1/5. It's the same like as divided by 5, which gave me the constant rate I was looking for, which is, I put it into calculator, gave me k equals negative 0.0073. So now that I have the k value, to figure out the next question, which is going to be asking me, it's going to be asking me to plug in values into the formula. Now I have the k figured out. Now I just have to plug in values for time, for t, and that's going to give me, let's see, temperature, I think. What's the question? They asked me a question somewhere. Okay, comes to here, 7 minutes. So now I have the formula. The formula I'm using is 39. U of t equals 39 minus 28 e to the kt power. So now I just plug in a value. They wanted me to plug in the value of 7 minutes. So I would find out what temperature the thermometer would be at 7 minutes. So now that I have the k figured out, I plug in the value for k, I plug in the value for t, there's k and there's t values, and I substitute it into the equation and just solve with a calculator. So I plug in 39 minus 28e caret, like raised to the parentheses negative 0.0073 parentheses times 7, like that's in the power part and the exponential part. These parts here, the little ones, the little numbers are the exponential parts, and that gave me 12.39 degrees after 7 minutes. So the temperature of the thermometer would read 12.39 degrees after 7 minutes. Now I could also graph the formula, which is y equals 39 minus 28e raised to the kt power, which I could just put the values there, raised to negative 0.007 times t, or like x times x, and then that would like graph. I would just input it into the window and then I would hit graph, and it would show me a graph over time, the temperature of the thermometer as it would warm up to the surroundings in this case. So thus was Newton's law of cooling an example of that.